Hello, everyone. My name is Bob Seaman with KPM Analytics. My title is Director of Product Marketing, and I will be your instructor for this UCal4 calibration course. So we've designed this course for our users, for our customers, for our specialists around the world that will be using UCal4 to develop or manage or expand calibrations. So we've designed this course into various lessons, and the lessons will give you the background to understand the theory and the concept of what we're doing in near-infrared spectroscopy, especially with Unity near-infrared instruments and UCal4 software. The lessons are followed by exercises, and the exercises are designed to be hands-on activities with our software that help put some of those principles and theories into work to develop robust, stable, and high-performance calibrations. So these two work hand in hand. A little bit about my background. I started in near-infrared in late 80s, so 30 years ago. And I started out as a user with a plant breeding biotech company. Spent about 10 years in a lab using near-infrared, and from that point on, in the late 90s, I've been working with analytical instrument companies. I've had quite a few number of different roles, from product manager, project manager, various hardware, software projects, customer support, and through that time, I've been involved with a lot of applications. So one thing I am not is I am not a chemometrician. I'm not a statistician. Nor am I a spectroscopist. So I would describe myself as an NIR enthusiast with a lot of experience developing applications and calibrations for near-infrared. And that's the perspective that I'm going to try to present through this course. We will talk about theory and principles in the background, but it's to provide a context and an understanding so that we can make the right decisions and create, robust, high-performance near-infrared calibrations. There are a lot of other resources out there. If you're interested in spectroscopy, if you're interested in chemometrics, you can let me know, send me a note. I would be happy to provide those references. But I wanted to, present this course as a practical course to help you develop your NIR calibration. Okay, with that, I'm going to jump into lesson one, and lesson one is going to be about spectroscopy. It gives us a little bit of the background so that we can hopefully make good decisions, and it will guide our calibration development. It also will help us be more efficient, because if we understand the principles of near-infrared and what's happening with our instruments and with our samples, it's going to help us make good decisions and get to our endpoint faster. So I talked a little bit about the course outline. So it is broken into lessons and exercises. And these exercises, it's going to be much more granular than this, but we will start out with a series of lessons to provide the background. And this is a general outline. So we'll talk about spectroscopy, talk about how, historically instruments have been designed to make use of this phenomena in the near-infrared spectrum. Talked a little bit about data analytics and some of the principles and some of the things to worry about, and in general, what we're doing and how it works. Talk a little bit about sample management, and then we'll talk about calibration development and specifically what happens during the regressions, how we can change the incoming raw spectra, the raw source, the various statistical ways we can evaluate it, and just in general calibration development. And then we've got a short part in about instrument matching, and then I've got a lecture towards the end about advanced topics. So we'll touch on some of the advanced topics, and these features that are available in CU Cal 4 software. So the goal really is I want everybody to understand the basics of near-infrared theory. They need to understand, everybody needs to understand, what type of a measurement we're making, what the instrument actually sees, and how we're using those data. Talk a little bit about calibration planning, development, and monitoring. So this is the whole procedure of starting from scratch, developing a calibration, and then the ongoing maintenance of the calibration. Along the way, we'll be talking about statistics and how we're evaluating what we're doing. And throughout this, we're going to I will try to be very concise about how I'm describing things in the language and the terms that we're using. It provides an understanding for what we're doing, but also when you're talking with colleagues or when you're talking with some of my KPM colleagues, it just provides a common language that we can use to describe what we're working on. So spectroscopy, what is near-infrared and how does it work? So near-infrared spectroscopy is an analytical technique. Like any other ones, it's got strengths and weaknesses. But this one is based on our ability to draw information from the response of light impinging on our samples, okay? And that phenomenon in and of itself does nothing, but we can combine that with some pretty sophisticated math, and we can pull information out of this spectra and out of this interaction, and we can create a relationship between this interaction with our sample and our constituents of interest. In fact, one of the things that's interesting is that the progress of near-infrared is pretty closely tracked to the progress of personal computers. So towards the middle 80s, it started becoming a really commercially available technique. And through the 80s and through the 90s is really where we started getting computers that were fast enough that we could do some of these chemometrics in a reasonable amount of time. So this is what near-infrared spectroscopy is. So why are we using near-infrared and what is the significance of that? Well, near-infrared is just a part of the electromagnetic spectrum. So like any other part of the electromagnetic spectrum, it's got certain properties related. So a couple of these properties are important. One of this is that energy is inversely related to wavelength. So the longer the wavelength, the lower the amount of energy that's carried by electromagnetic waves or information. Shorter wavelengths have higher energy. So this is energy that will interact not very well with a sample. In fact, it just, in general, will penetrate through the sample more. Ionizing wavelengths below the ultraviolet interact with nuclei. So these are X-rays, gamma rays, they're just penetrating right through. We don't get a lot of information from that. It's not useful for us. Ultraviolet in these wavelength ranges interacts with electronic energy levels. Again, for what we're trying to do, that's not very useful for us. If we jump to the other side and we start going into an IR, well, near infrared and then IR, we start interacting with chemical bonds. And we'll find out later in this lecture that that's a portion of the electromagnetic spectrum that is giving us information that relates to our constituents of interest. So this is really where it starts getting interesting and providing useful information for us. Beyond that, we start getting into microwave and radio waves. And again, that's really not useful for what we're trying to do in the lab. So this is the area of the electromagnetic spectrum. You can see that in near infrared, we're right in this. We're right above the visible, slightly longer wavelengths than the visible, before IR and microwaves and radio bands. So what's happening with the near-infrared spectrum? We've got several different slides to talk about this, but organic molecules exist in various energy states, including the bonds. And these bonds have certain vibrational energies. And based on the energies and the resonant frequencies of these bonds, they can absorb specific NIR wavelengths for these various bonds. And we know that organic molecules are the building blocks of all food products. They're the building blocks of all of our agricultural products. And this is primarily what we're going to be interested in with our measurements in NIR and Unity. So the organic bonds have these different bond types. We've got hydroxyls or OH bonds, CH bonds, NH bonds, CN bonds, NO bonds, and CO bonds. So these are various types of bonds. And if we go back to our organic chemistry, we know that these bonds have various strengths. They even have different distances. There's also different ways that these bonds are formed. So each one of these, from an absorbance perspective, or how they interact with near-infrared light, each one of these have different resonant frequencies or resonant wavelengths that absorb. So we'll talk about this later on, but one of the things that we can speculate on, and is in fact true, is that the more bonds that we have, the more that light is absorbed. So if we've got a particular absorbance of a CH bond, the more CH bonds that are present in our sample, the more the light will absorb at that wavelength. So bonds have characteristic frequencies that do not change if analytical conditions do not change. So this is not a simple one wavelength absorbance curve that you might find in a simple colorimetric test. This becomes a mess, as we're going to talk about in a little bit. But on a very micro level, each one of these bond relationships has a characteristic frequency where it absorbs. And beyond that, it's got resonant and harmonic frequencies also, mathematical multiples, where the light will also be absorbed. And it's possible to use this to, in a way, measure how many, for example, CH bonds we have, and relate that eventually to our property or constituent of interest. So at a very fundamental level, this is what we're doing in near-infrared. So we've chosen near-infrared for a number of different reasons, but in this general area of the electromagnetic spectrum, the light energy is interacting with bonds, and we can map that again to our constituent of interest. So if we look at the different wavelength ranges in near-infrared, these are broad generalities. I hesitate to even put these tables out because it simplifies a very complex picture. But in general, you can say that up around in the upper wavelength ranges in the near-infrared area, we've got CH combination bonds that are absorbing. A little bit further down, we're getting into hydroxyls and amines. We start getting into an overtone region through these wavelength ranges. Further down, we start getting combination bands and second and third overtones. So you can see, for example, even the CH bonds absorb in various areas in the near-infrared spectrum. Another way to look at that is in this upper wavelength area, we see these bonds, CH, and we can relate these in some way to these types of chemical compounds that are out there. In this wavelength area, a little bit further down, we've got amine or NH bonds. We can see proteins and amino acids. It's a very strong area if we're doing protein measurements. And further down, again, we're just looking at the upper area of the near-infrared region. 1900 to 2000, we can see hydroxyls or OH bonds. So we're looking at moistures, alcohols, sugars, starches, polymers, things like that. So this is just an example in a very broad fashion. Again, it's much more complex than this, of how the different areas of the near-infrared spectrum relate to these bonds and to these organic compounds. So in our instruments, the absorbance that we're measuring occurs when the near-infrared light energy interacts with our bonds. Okay, and we create a plot. We create a spectrum plot. And on the x-axis, we see the wavelength. And on the y-axis, we see the energy that's been absorbed, or the absorbance, okay? So on the y-axis, it'll be absorbance units. We'll show how to calculate that in a second. And on the x-axis, we will see all the wavelengths. For our instruments, our scanning monochrometers. So we collect a full spectrum of information. And in most cases, unless you're really good at this, it's really difficult to relate a given wavelength to a single constituent. Quick note about frequency and wavelength. If we think back to physics, frequency and wavelength are mathematically related by the speed of light. So the speed of light is a constant. So we can say that frequency has some sort of a constant over wavelength. And the constant is dependent on the units of frequency or wavelength. In speaking about near infrared, generally we talk about wavelengths and we use nanometers. If you're doing other areas of spectroscopy or other techniques and technologies, you might be talking about frequency or wave numbers. So for what we're doing, we are going to measure our wavelength scale in nanometers, and that's our units of measurement. So how are these related? If you remember, in a couple of slides back, we said that the larger the wavelength, the lower the energy, okay? So I like this slide because it relates the different properties of this area of the electromagnetic spectrum. And this also kind of infers or describes why near infrared is kind of the best of all worlds. It's the best compromise. It's the best region of the electromagnetic spectrum for what we're trying to do. So we know that wavelength and frequency are inversely proportional. So in this graph of the electromagnetic spectrum, wavelength is increasing this way to the right, frequency is increasing to the left. Okay. Another function of the electromagnetic spectrum is resolution, or the sharpness, or the differentiation we can make among these different peaks and absorbances. Resolution increases as the wavelength goes up, but increases to the right. Conversely, the bond overlap and the width of these bonds increases as the wavelength goes down. So we've got very sharp, nicely defined peaks up in the infrared region, whereas down in the near infrared, we start getting broad overlapped peaks, which also confounds the picture that we're looking at. If we look at absorptivity, or the interaction that this light has with the sample, the absorptivity goes up as you increase the wavelength. So for example, if you're doing a transmission measurement and you start working from near infrared up towards the infrared, the path length is necessarily shorter because the absorptivity increases and the energy decreases. Conversely, as the energy increases, our penetration depth increases as we get to shorter wavelengths. So if we are doing a transmission measurement, for example, if you're doing whole grain analysis, generally you're working down towards the visible region because it's got higher energy and higher penetration depth. So this slide just describes how there's no perfect region of the spectrum, and each area it's a compromise between some advantages and disadvantages. So in summary, why the NIR regions? Well, we get the highest energy for looking at bonds. We can look at coarse materials. So especially for working in reflectance, this is a great area where we get the right interaction with the sample, and we can work with ground samples and even coarsely ground samples. We get decent penetration. So it means that the light is actually interacting with the sample. So the penetration, if you remember, is it's a compromise between penetration and the absorptivity of the energy. So this region gives us decent penetration and interaction with the sample. pretty forgiving with regards to sample preparation as far as scatter properties and things like that. And some of the other regions require much more sample handling. For example, as you're moving up into the wavelength area, upper wavelength regions up towards IR, the energy is lower such that you need really thin and narrow path lengths. So NIR happens to just be in this kind of a sweet spot. What does it look like? Well, this is just I'm not sure what product this is, some sort of a food product. But if you remember, we were talking about a plot of a spectrum. On the y-axis, we've got the absorbance. And on the x-axis, we've got the various wavelengths that we're scanning and we're collecting. So if you notice, there's a general slope. That's a scattering effect. A lot of times that's correlated with particle size, for example. You can see the broad peaks, okay? There's no sharply defined peaks like we might remember back from organic chemistry days if we're looking at IR spectra. And you can do characteristic almost fingerprints or fingerprint spectra of samples. We don't get that. We get broad overlapped peaks in the near-infrared area. And if you look at this and if you think about it, you can also see some repetition. If you remember a couple of slides back, I described that the CH bonds, for example, are found in multiple areas, multiple wavelength areas. Well, there is a repetition of information through this wavelength range. This one is looking at 1200 to 2400 nanometers. You can see that the information here looks very similar to the information here. And likewise, these are replicated here. For example, there's a moisture peak right here, and there's a moisture peak right here. So there is redundant information in the near-infrared spectra, but the various areas have different properties. And our math, as we will see, will actually use the entire wavelength area, the entire spectrum, and it will, through the regression process, determine the areas of the spectra that are adding either positively or negatively to the measurement of our constituent of interest. So this is what the raw data looks like. And this is what we will be spending the next lectures and exercises on, is how to collect and utilize this raw data to measure our constituents of interest. So if we look at what's going on, at each wavelength, we've got an interaction with the light. So our sample absorbs light according to the amount of bonds that are present, okay? And these bonds are doing various things. They're stretching, they're wiggling, they're rotating. So even to a specific bond type, there are various frequencies and wavelengths that are absorbing. So again, it's a pretty complicated mix. So we actually measure the light that is not absorbed, okay? So we're measuring the reflectance, the reflected light. And then from that, we can compute the amount of energy that has been absorbed. And the absorbance formula looks like this. So it's the negative log of our sample energy minus the dark energy over our reference energy minus the dark energy. So every time that we are making a measurement in our instrument, one of the things we look at is the background energy that is hitting the detector. This is known as the dark values. So this is just a background signal that is happening through your instrument. So we take the intensity of the energy from your sample. We always select out the dark. That's our numerator. The energy of the reference, we use a dual beam system. So we always refer our sample spectrum to a reference spectrum to make it more consistent. So the reference spectrum also gets the dark energy removed. So this ratio, we take a negative log and we can determine what the absorbance is at that wavelength. So the absorbance at each individual wavelength is the sum total of all of the interaction that light is happening with the sample. So we're looking at the interaction with all of the bonds, everything that's happening, along with physical or optical happenings, scatters and things like that. But in general, we know that at that wavelength, if we get more absorbance, more bonds are present. If we've got less energy coming back, we are absorbing more. So we can use this relationship to figure out our concentration. So there's a law, a principle that's out there, that Beers-Lambert law, that says a concentration is linearly proportional to absorbance. This is a theory. There are tons of papers out there that can describe slight deviations from this, but it's a principle. So in general, the formula looks like concentration equals absorptivity times the path length times absorbance. So we're working in reflectance in general with our instruments. So the interaction that we have with the light with the sample is highly variable. If you think about the light penetrating a sample, it's normally about 1 millimeter or so, but it's interacting to various depths. So there's no consistent path length, okay? The J, the absorbance value, is at a particular wavelength, and then there's some sort of a constant in this. So the formula assumes a single wavelength, no other constituent is there, and a consistent path length. Well, these are not completely valid assumptions for what we're doing. The original Beer's law looks like this. It's a very simple formula. Absorbance equals the absorbance coefficient times the path length times the concentration. This, again, is a simplified picture of what we're doing, but in practice, it really looks like this. You know, we're using multiple wavelengths. We've got varying path lengths. We will include the fact that each absorbance contains inferences or indicators to our desired constituents. So we know that not all of the principles of Beers-Lambert law are being adhered to, but one thing that is true, and we will retain, and this is really the core of what we're doing, is we will retain the idea that concentration is indeed proportional to absorbance. And you'll find that it is, okay? So this is the fundamental part of what we're going to be doing. We're actually looking at the absorbance of bonds. We're interacting light with the sample. We're going to go through, you know, several complicated steps and some very fancy math. And at the end of it, we're going to relate it to our constituent of interest, let's say protein. But at the core of this, understand that we're looking at the absorbance of near-infrared light, and we're going to relate that to the concentration of our constituent or parameter of interest. One of the things that I want to do to end this lecture is I want to talk about a couple of cautions or things to keep in mind when you're working through near-infrared. First one is near-infrared should be considered as a parts per 100 or a percent method. So this is, near-infrared in general is not a good method for trace analyses. So in some cases, if we've got a very visible constituent, we can get down to the parts per 1,000 measurements. It depends on how visible or how unique that molecule or compound of interest is in the near-infrared spectrum. But in general, this is looking in a percent type of a scale. In extremely rare cases, you can get down to parts per million. I've never personally worked on those. So don't think of near-infrared as a trace and that analytical method. Another thing to think about is spiking or artificially mixing samples. This can be done with a lot of other analytical techniques, but in general, it does not work with near-infrared. We're relying on the relationships of our samples and specifically looking at these chemical bonds. And the chemical bonds vary even depending upon the environment that these various molecules find them in. And in general, when you're making artificial samples or you're spiking, these molecules are not found and do not look the same as they do in a natural product. So there are a number of cases where we can spike samples. One of them I can think of is seasoning, for example, in snack food. We can make artificial samples based on weight with seasoning, but what we're doing there is we're actually mimicking what happens in the production of snack foods. We're applying seasoning for our samples. But, for example, we can actually measure difficult things like we can look at various elements or minerals, for example, in, for example, forages. And if you look at them in their natural state, we can see the relationship of these minerals to the various protein and other complexes that hold the minerals, and we can make a decent measurement in a good relationship. But adding any other minerals or supplements or whatever to the forage is completely invisible to near infrared, and it's not going to be seen at all. So just a little bit of a caution, be very careful about spiking or making artificial mixtures. Another caution in near infrared, and this we'll get into when we get into the analytics of the chemometrics part of this, but a big issue with near infrared can be overfitting. And overfitting is when your model performs better than it will in real life. In other words, your artificial, when you go through the calibration process, you are not doing a good approximation of how the model will apply or work in real life. And especially early in the technology, most of the negative stories that you saw were people taking a very simplified look at an analytical situation, extrapolating their performance from a very small calibration set, and it was in fact overfit and didn't perform well in the real life. So we've got tools for doing this, and we'll describe that through this course, but just a note of caution. And some of the negatives you might hear about near infrared, in general, it's where people try to push too far. They aren't evaluating their models correctly, and they're overfitting. Okay. A couple of final thoughts also, things that I've learned over time in spectroscopy. You will hear me repeat these through the various lessons and exercises we go through, but always remember that near infrared is a secondary measurement. Okay, there's nothing going on in our NIR instruments that have any idea what protein is. So we are using the instruments to look at the interaction that near infrared light has with our samples. That interaction is based on bonds. Those bonds are found in our molecules of interest. And we are using good analytical techniques and very sophisticated math to make that relationship. So always remember it's a secondary measurement. Another key part is that near infrared is very good at interpolating, but it's not very good at extrapolating. And this relates to the last point also, but if during your calibration exercise, calibration process, if you've exposed that calibration process to the sample variation you expect to see, so that your unknowns that you're analyzing afterwards fall within that calibration set, I'm going to trust the NIR calibration within its performance statistics. In fact, in most cases, I'm going to trust the NIR more than the reference method that it's based on. Near infrared is in general very precise and very repeatable, but it's not very good at extrapolating. So this relates to the last point. And this is just something that I learned over time. It seemed like in the beginning of near infrared, we were all fascinated with the math and the regressions, and computers were getting faster and things like that. But as time goes on, I've come to realize that the majority of the difficult part of making a good NIR calibration is finding the right samples. So I wrote here, if you've got the wrong samples in your calibration set, it's going to be very difficult to get a good, robust calibration. Conversely, if you have the right samples and good reference data, it's going to be relatively easy to get a robust and reliable calibration. The hard part is getting the right samples. So with that, that will be the end of the first lesson. Let's move on to number 2. Thank you, everybody.